Power quality refers to the characteristics of electrical power, including voltage, frequency, and harmonics. Power conditioning devices are employed to enhance power quality by mitigating disturbances and upholding a consistent and dependable power supply. A chromatograph is a laboratory instrument utilized for separating and analyzing chemical mixtures. It necessitates a stable and uninterrupted power supply to guarantee precise results. To address power quality concerns and ensure dependable chromatograph operation, contemplate implementing power conditioning measures. Firstly, a voltage regulator stabilizes voltage levels, preventing fluctuations that could harm sensitive equipment. Secondly, a harmonic filter suppresses harmonics, diminishing distortions in the power supply. Thirdly, a surge protector safeguards equipment against transient voltage spikes and lightning strikes. It is recommended to conduct a power quality assessment to pinpoint specific disturbances present. Select power conditioning devices predicated on the assessment outcome. Install and configure the devices accurately to ensure optimal performance. Routinely inspect and maintain the power conditioning system to ascertain its effective functioning. Voltage fluctuations are variations in the voltage level of an electrical power supply. These fluctuations can be caused by various factors, including changes in the load on the power grid, starting and stopping of large electrical equipment, and faults in the power system. Voltage fluctuations can have adverse effects on sensitive electronic equipment, such as computers, medical devices, and industrial control systems. These effects can include data loss, equipment malfunction, and reduced equipment lifespan. Harmonics are distortions in the waveform of an electrical power supply. They are caused by nonlinear loads, such as electronic devices, variable frequency drives, and arc furnaces. Harmonics can cause a variety of problems, including increased energy consumption, equipment overheating, and interference with communication systems. Transient spikes are short-duration, high-voltage surges that can occur on an electrical power supply. They are typically caused by lightning strikes, switching of electrical equipment, and electrostatic discharge. Transient spikes can damage or destroy sensitive electronic equipment. A voltage regulator is an electrical device that maintains a constant voltage level. It does this by adjusting the amount of current that flows through the device. Voltage regulators are used in a variety of applications, including power supplies, battery chargers, and automotive electronics. Harmonic filters are electrical devices that reduce the level of harmonics in an electrical power supply. They do this by creating a low impedance path for the harmonic currents to flow through. Harmonic filters are used in a variety of applications, including industrial plants, commercial buildings, and data centers. A surge protector is an electrical device that protects equipment from transient voltage spikes. It does this by diverting the excess voltage to ground. Surge protectors are used in a variety of applications, including homes, offices, and industrial facilities. A power quality assessment is a process of measuring and analyzing the characteristics of an electrical power supply. This assessment can help to identify potential power quality problems, such as voltage fluctuations, harmonics, and transient spikes. The results of a power quality assessment can be used to select the appropriate power conditioning devices to mitigate these problems. To install and configure the devices accurately to ensure optimal performance, firstly, review the manufacturer's instructions carefully before installing any power conditioning devices. Secondly, ensure that the devices are properly grounded. Thirdly, connect the devices to the electrical power supply according to the manufacturer's instructions. Fourthly, configure the devices according to the manufacturer's instructions. Routinely inspect and maintain the power conditioning system to ascertain its effective functioning. Firstly, visually inspect the devices for any signs of damage. Secondly, check the connections to ensure that they are tight and secure. Thirdly, test the devices to ensure that they are functioning properly. Fourthly, clean the devices regularly to remove any dust or debris. By implementing these measures, you can improve power quality, minimize disturbances, and ensure reliable operation of your customer's chromatograph. This will support their R&D experiments and prevent data loss or damage to equipment. Power quality issues can arise from various sources, both within the customer's facility and from the external power grid. Internal sources can include the operation of heavy machinery, switching power supplies in electronic equipment, and improper wiring. External sources can include lightning strikes, utility grid switching, and faults in the power system. A power quality assessment involves measuring and analyzing various parameters of the electrical power supply, such as voltage, current, frequency, harmonics, and transients. This assessment can be performed using specialized equipment, such as power quality analyzers and oscilloscopes. The results of the assessment can help to identify the specific types of power quality disturbances that are present and their severity. Based on the assessment results, appropriate power conditioning devices can be selected to mitigate the identified disturbances. For example, if voltage fluctuations are a major concern, a voltage regulator can be used to stabilize the voltage level. If harmonics are present, a harmonic filter can be used to reduce the level of harmonics. If transient spikes are a concern, a surge protector can be used to protect equipment from these spikes. The installation and configuration of power conditioning devices should be performed by qualified personnel in accordance with the manufacturer's instructions and applicable electrical codes. Proper grounding is essential for the effective operation of these devices. Regular inspection and maintenance are necessary to ensure that the power conditioning system continues to function effectively. This includes visually inspecting the devices for any signs of damage, checking the connections to ensure that they are tight and secure, and testing the devices to ensure that they are functioning properly. In addition to the specific power conditioning devices mentioned, other measures can be taken to improve power quality. These include using shielded cables to reduce electromagnetic interference, separating sensitive equipment from noisy equipment, and implementing proper grounding techniques. Power conditioning is crucial for modern electronics due to the increasing sensitivity of electronic devices to power quality issues. Fluctuations in voltage, frequency variations, harmonics, and transient voltages and noise can have adverse effects on electronic equipment. These effects can include data errors, equipment malfunctions, reduced lifespan, and even permanent damage. Power conditioning equipment is used to provide a clean and stable power supply, protecting sensitive electronics from these power quality issues. There are various types of power conditioning equipment available, each designed to address specific power quality issues. Firstly, voltage regulators maintain a stable voltage level, preventing fluctuations that can damage sensitive equipment. Secondly, line conditioners filter out noise and voltage fluctuations, providing a cleaner power supply. Thirdly, surge protectors protect equipment from transient voltage spikes and lightning strikes. Fourthly, uninterruptible power supplies provide backup power in the event of a power outage, ensuring continuous operation of critical equipment. When selecting power conditioning equipment, it is important to consider the specific needs of the application, the power requirements of the equipment being protected, the type of power quality issues that are present, and the level of protection required should all be taken into account. It is also important to choose power conditioning equipment from a reputable manufacturer and to ensure that it is properly installed and maintained. Regular maintenance of power conditioning equipment is essential to ensure that it continues to function effectively. This includes checking the equipment for any signs of damage, cleaning the equipment regularly, and testing the equipment to ensure that it is functioning properly. Power conditioning is an essential investment for protecting sensitive electronics from power quality issues. By providing a clean and stable power supply, power conditioning equipment can help to prevent data errors, equipment malfunctions, reduce lifespan, and even permanent damage. Proper grounding is a critical aspect of electrical safety and power quality. A grounding system provides a low impedance path for fault currents to flow back to the source, which helps to protect people and equipment from electrical shock and damage. A properly designed and installed grounding system can also help to reduce noise and improve power quality. There are several different types of grounding systems, each with its own advantages and disadvantages. The most common type of grounding system is the equipment grounding system, which connects all of the non-current carrying metal parts of electrical equipment to ground. This helps to ensure that if a fault occurs, the fault current will flow back to the source and trip a circuit breaker or fuse, de-energizing the equipment and preventing electrical shock. Another type of grounding system is the system grounding system, which connects the neutral point of the power source to ground. This helps to stabilize the voltage and reduce noise. The NEC National Electrical Code provides detailed requirements for grounding electrical systems. These requirements are designed to ensure that grounding systems are safe and effective. Some of the key requirements include the following. Firstly, all electrical equipment must be properly grounded. Secondly, the grounding system must be sized adequately to carry the maximum fault current. Thirdly, the grounding system must be installed in accordance with the NEC. Regular inspection and maintenance of the grounding system are essential to ensure that it continues to function effectively. This includes visually inspecting the grounding system for any signs of damage such as corrosion or loose connections. It also includes testing the grounding system to ensure that it is providing a low impedance path for fault current. Improving power quality requires a comprehensive approach that addresses both the sources of power quality disturbances and the susceptibility of equipment to these disturbances. Some of the key steps that can be taken to improve power quality include the following. Firstly, identify the sources of power quality disturbances. This can be done through power quality monitoring and analysis. Secondly, mitigate the sources of power quality disturbances. This can be done through the use of power conditioning equipment, such as voltage regulators, harmonic filters, and surge protectors. Thirdly, protect sensitive equipment from power quality disturbances. This can be done through the use of surge protectors, uninterruptible power supplies, and other power conditioning equipment. Fourthly, implement proper grounding techniques. This can help to reduce noise and improve power quality. Fifthly, regularly inspect and maintain electrical equipment. This can help to prevent power quality problems from developing. Power quality monitoring is the process of measuring and analyzing the characteristics of electrical power to identify and diagnose power quality problems. Power quality monitoring can be used to identify voltage sags, voltage swells, harmonics, transients, and other power quality disturbances. Power quality monitoring equipment typically includes voltage and current probes, a data logger, and software for analyzing the data. The data logger records the voltage and current waveforms over time, and the software analyzes the data to identify power quality disturbances. Power quality monitoring can be performed on a continuous basis or on an as-needed basis. Continuous power quality monitoring is typically used in critical applications such as data centers and hospitals. As-needed power quality monitoring is typically used to troubleshoot power quality problems. Power quality analysis is the process of interpreting power quality monitoring data to identify the causes of power quality problems. Power quality analysis typically involves examining the voltage and current waveforms, calculating harmonic distortion levels, and analyzing transient events. Power quality analysis can be performed manually or using software tools. Manual power quality analysis involves examining the voltage and current waveforms and calculating harmonic distortion levels. Software tools can automate the process of power quality analysis and provide more detailed information about power quality disturbances. Power quality mitigation is the process of reducing or eliminating power quality problems. Power quality mitigation techniques include the use of power conditioning equipment, such as voltage regulators, harmonic filters, and surge protectors. Power quality mitigation techniques also include the implementation of proper grounding techniques and the regular inspection and maintenance of electrical equipment. Voltage regulators are used to maintain a stable voltage level, which can help to prevent voltage sags and voltage swells. Harmonic filters are used to reduce harmonic distortion levels, which can help to improve power factor and reduce equipment overheating. Surge protectors are used to protect equipment from transient voltages, which can be caused by lightning strikes or switching events. Proper grounding techniques can help to reduce noise and improve power quality. Regular inspection and maintenance of electrical equipment can help to prevent power quality problems from developing. Transient voltage surge suppressors (TVSS) are devices designed to protect electrical and electronic equipment from voltage spikes. These spikes, often caused by lightning strikes, power grid switching, or even the operation of heavy machinery within a facility, can damage or destroy sensitive electronic components. TVSS devices work by diverting excess voltage away from the protected equipment. When a voltage spike occurs, the TVSS quickly clamps the voltage to a safe level, preventing it from reaching the equipment. There are several different types of TVSS devices available, each with its own characteristics and applications. Firstly, surge arresters are typically used to protect electrical service entrances and other high-energy locations. Secondly, surge suppressors are typically used to protect individual pieces of equipment or branch circuits. Thirdly, whole-house surge protectors are installed at the main electrical panel and provide protection for the entire home. When selecting a TVSS device, it is important to consider the following factors. Firstly, the voltage rating of the device. Secondly, the surge current capacity of the device. Thirdly, the clamping voltage of the device. Fourthly, the type of equipment being protected. It is also important to choose a TVSS device from a reputable manufacturer and to ensure that it is properly installed. Proper installation of a TVSS device is essential to ensure that it provides adequate protection. The device should be installed in accordance with the manufacturer's instructions and all applicable electrical codes. It is also important to ground the TVSS device properly. Regular maintenance of a TVSS device is also important. The device should be inspected regularly for any signs of damage. If the device has been subjected to a large surge, it should be replaced. Power factor correction is the process of improving the power factor of an electrical system. Power factor is a measure of how efficiently electrical power is being used. A power factor of 1.0 indicates that all of the electrical power is being used effectively, while a power factor of less than 1.0 indicates that some of the electrical power is being wasted. Low power factor can result in increased energy costs, reduced equipment capacity, and voltage drops. Power factor correction is typically achieved by adding capacitors to the electrical system. Capacitors store electrical energy and release it back into the system when needed. This helps to offset the effects of inductive loads such as motors and transformers, which cause the power factor to be low. The amount of power factor correction needed depends on the specific characteristics of the electrical system. A power factor correction study can be performed to determine the optimal amount of capacitance to add to the system. Power factor correction capacitors should be installed by a qualified electrician. The capacitors should be properly sized and installed in accordance with all applicable electrical codes. Harmonic distortion is a type of power quality disturbance that can cause a variety of problems in electrical systems. Harmonics are currents or voltages that are integer multiples of the fundamental frequency of the power system, which is typically 60 Hz in North America. Harmonic currents can cause equipment overheating, voltage distortion, and interference with communication systems. Harmonic voltages can cause equipment malfunction and reduce equipment lifespan. Harmonic distortion is typically caused by nonlinear loads such as electronic devices, variable frequency drives, and arc furnaces. Nonlinear loads draw current in a non-sinusoidal manner, which creates harmonics. Harmonic filters are used to reduce harmonic distortion levels in electrical systems. Harmonic filters work by providing a low impedance path for harmonic currents to flow, which prevents them from flowing through the rest of the electrical system. There are several different types of harmonic filters available, each with its own characteristics and applications. Firstly, passive harmonic filters consist of inductors, capacitors, and resistors that are tuned to filter out specific harmonics. Secondly, active harmonic filters use electronic components to actively cancel out harmonic currents. Thirdly, hybrid harmonic filters combine passive and active filtering techniques. The selection of a harmonic filter depends on the specific characteristics of the electrical system and the type of harmonic distortion that is present. A harmonic analysis study can be performed to determine the optimal type and size of harmonic filter for the system. Harmonic filters should be installed by a qualified electrician. The filters should be properly sized and installed in accordance with all applicable electrical codes. Uninterruptible power supplies, UPS, are devices that provide backup power in the event of a power outage. UPS systems are typically used to protect critical equipment such as computers, servers, and medical devices from data loss and downtime. A UPS system consists of a battery, a charger, and an inverter. The battery stores electrical energy, the charger keeps the battery charged, and the inverter converts the battery's direct current DC voltage to alternating current AC voltage to power the equipment. There are several different types of UPS systems available, each with its own characteristics and applications. Firstly, standby UPS systems are the simplest type of UPS system. They provide backup power only when the power goes out. Secondly, line interactive UPS systems provide some voltage regulation and surge suppression in addition to backup power. Thirdly, online UPS systems provide continuous power conditioning and backup power. The selection of a UPS system depends on the specific needs of the application. Factors to consider include the power requirements of the equipment being protected, the amount of backup time required, and the level of power conditioning needed. UPS systems should be installed and maintained by a qualified technician. The batteries in a UPS system should be replaced every few years. Power distribution units, PDUs, are devices that distribute electrical power to multiple devices. PDU are typically used in data centers and other environments where there are a large number of devices that need to be powered. A PDU typically consists of a power inlet, a circuit breaker panel, and a number of outlets. The power inlet connects the PDU to the electrical power source. The circuit breaker panel protects the devices connected to the PDU from overcurrents. The outlets provide power to the devices. There are several different types of PDU available, each with its own characteristics and applications. Firstly, basic PDU provide only power distribution. Secondly, metered PDU provide power distribution and also measure the amount of power being used by each outlet. Thirdly, switched PDU provide power distribution and also allow the user to remotely switch the power to each outlet on or off. Fourthly, intelligent PDU provide power distribution, power measurement, and remote power switching, as well as environmental monitoring and other advanced features. The selection of a PDU depends on the specific needs of the application. Factors to consider include the power requirements of the devices being powered, the number of outlets needed, and the level of monitoring and control required. PDU should be installed and maintained by a qualified electrician. Shielded power cables are electrical cables that have a layer of shielding around the conductors. The shielding is typically made of a conductive material, such as copper or aluminum. Shielded power cables are used to reduce electromagnetic interference, EMI, which can disrupt the operation of sensitive electronic equipment. EMI can be caused by a variety of sources, such as radio transmitters, microwave ovens, and electrical motors. Shielded power cables work by attenuating the electromagnetic fields that are emitted by these sources. The shielding absorbs the electromagnetic energy and converts it into heat, which is then dissipated. Shielded power cables are typically used in environments where there is a high level of EMI, such as hospitals, laboratories, and industrial facilities. They are also used in applications where it is important to protect sensitive data from being intercepted. When selecting shielded power cables, it is important to consider the shielding effectiveness of the cable. The shielding effectiveness is a measure of how well the cable attenuates electromagnetic fields. The higher the shielding effectiveness, the better the cable will protect against EMI. Shielded power cables should be installed by a qualified electrician. The shielding should be properly grounded to ensure that it is effective. Proper wiring practices are essential for ensuring the safety and reliability of electrical systems. Improper wiring can cause a variety of problems, such as electrical shocks, fires, and equipment damage. Some of the most important proper wiring practices include the following. Firstly, use the correct size wire for the application. The size of the wire must be large enough to carry the current that will be flowing through it. Secondly, use the correct type of wire for the application. The type of wire must be suitable for the environment in which it will be used. Thirdly, make sure that all connections are tight and secure. Loose connections can cause overheating and arcing, which can lead to fires. Fourthly, ground all electrical equipment properly. Grounding provides a path for fault currents to flow back to the source, which helps to protect people from electrical shock. Fifthly, protect circuits with circuit breakers or fuses. Circuit breakers and fuses are designed to interrupt the flow of current in the event of an overcurrent or short circuit. Sixthly, follow all applicable electrical codes. Electrical codes are designed to ensure the safety and reliability of electrical systems. Regular inspection and maintenance of electrical systems are essential for identifying and correcting any wiring problems. A qualified electrician should perform these inspections. The NEC National Electrical Code is a set of standards for the safe installation of electrical wiring and equipment in the United States. The NEC is developed by the National Fire Protection Association, NFPA, and is updated every 3 years. The NEC covers a wide range of topics, including wiring methods, overcurrent protection, grounding, and equipment installation. The NEC is adopted by most states and local jurisdictions in the United States. Compliance with the NEC is essential for ensuring the safety and reliability of electrical systems. The NEC is not a design manual, but it provides minimum requirements for safe electrical installations. Qualified electricians should be familiar with the NEC and should follow its requirements when installing electrical wiring and equipment. NEC Table 310.15b16 provides ampacity ratings for conductors based on their size, insulation type, and installation conditions. This table is used to determine the appropriate size conductor to use for a particular application. The ampacity of a conductor is the maximum amount of current that it can safely carry without overheating. NEC Article 250 covers the requirements for grounding and bonding electrical systems. Grounding is the process of connecting electrical equipment to the earth to provide a path for fault currents to flow back to the source. Bonding is the process of connecting together all of the metal parts of an electrical system to create a low impedance path for fault currents. Proper grounding and bonding are essential for protecting people from electrical shock and for preventing equipment damage. NEC Article 408 covers the requirements for switchboards and panel boards. Switchboards and panel boards are used to distribute electrical power to branch circuits. These articles provide requirements for the construction, installation, and overcurrent protection of switchboards and panel boards. NEC Article 500 covers the requirements for electrical equipment and wiring in hazardous locations. Hazardous locations are areas where there is a risk of fire or explosion due to the presence of flammable gases, vapors, or dusts. Article 500 provides requirements for the types of equipment and wiring that can be used in hazardous locations, as well as requirements for installation and maintenance. Power quality analyzers are instruments used to measure and analyze various parameters of electrical power systems. These analyzers help identify and diagnose power quality problems such as voltage sags, swells, harmonics, transients, and interruptions. Modern power quality analyzers typically measure voltage, current, frequency, power factor, harmonic distortion, and transient events. They also provide data logging capabilities to record power quality parameters over time for further analysis. When selecting a power quality analyzer, it is important to consider the following factors. Firstly, the types of parameters that the analyzer can measure. Secondly, the accuracy and resolution of the measurements. Thirdly, the data logging capabilities of the analyzer. Fourthly, the software that is included with the analyzer. Power quality analyzers are used by electricians, engineers, and other professionals to troubleshoot power quality problems, to verify the performance of electrical equipment, and to monitor the quality of electrical power. Routine maintenance of electrical equipment is crucial for preventing power quality problems and ensuring the reliable operation of electrical systems. Some of the key maintenance tasks include the following. Firstly, inspecting electrical equipment for signs of damage or wear. Secondly, cleaning electrical equipment to remove dust and dirt. Thirdly, tightening electrical connections to prevent overheating and arcing. Fourthly, testing electrical equipment to verify its performance. Fifthly, replacing worn or damaged components. Routine maintenance should be performed on a regular schedule, depending on the type of equipment and the operating environment. Keeping accurate records of maintenance activities is also important. Consulting with a qualified electrician or electrical engineer can help to develop a comprehensive maintenance plan. In conclusion, maintaining power quality requires a multifaceted approach that encompasses understanding power quality issues, utilizing appropriate power conditioning equipment, adhering to proper wiring practices, and conducting routine maintenance. By implementing these measures, one can ensure the reliable operation of sensitive electronic equipment and prevent costly downtime and data loss.